what questions do you have about the exam, either the format or the material?
I had a really quick, just like clarifying question from the last problem set. I was kind of confused on like the difference between RMS speed and just like average velocity.
Okay. Oh, I see the problem. Okay, can you still hear me okay?
Yeah.
Okay, so Alan's asked about the difference between RMS speed and average velocity, and basically there is no difference. I made that change in the wording of that problem because I hadn't introduced the idea of an RMS velocity, right? We talked about an RMS displacement, so a little bit complicated to fully answer that, but let me try to give a kind of simple answer. So we talked about the RMS displacement, x RMS, which is the square root of the mean of the displacement squared. And so you could talk about an RMS velocity, but I wouldn't use that term. So I think I would rather use the term the average speed associated with diffusion, which would be x RMS divided by the time over which you had allowed the diffusion to take place. Really separate from that, and again, in this course, we haven't used this term, and I won't use it on the exam, but you might encounter it in a different context. The RMS velocity is defined to be the square root of the average of the magnitude of the velocity squared. And so technically speaking, when we use the equipartition theorem to calculate a velocity, as you did in problems 1 and 9 on this most recent problem set, what you're really calculating is the average value of 1/2 mv squared, and you're using that to deduce a speed. So what you are really calculating here is the RMS velocity, but I think in this class we've just called it the average speed.
Okay, thank you.
Mm-hmm. Other questions? Can go down the list of topics and see if it elicits any questions, but you can just jump in at any point. So remember that this is a truly cumulative exam, and there definitely are questions on it from the material for our exams 1 and 2. But since exam 2, we've talked about momentum, the idea of impulse, be ready to derive the general law of conservation of momentum starting from Newton's second and third laws. 1D elastic collisions, the idea of analyzing collisions in the center of mass frame, which is kind of part of this, and then 2 and 3D collisions where the masses stick together at the start or the end. And I should have put this as part of this, sort of the opposite, meaning something that explodes, so where the objects start together and then explode apart. Angular momentum, general law of conservation of angular momentum, including how the angular momentum is changed by external torque.
Can we talk about like defining your system for momentum?
Sure.
And like kind of like the things associated with that?
So we're going back to regular momentum, right?
For both.
For both, okay, fine. So let's talk first in the context of regular momentum. So when I say the general law of conservation of momentum that I expect you to be able to derive, what I mean is that the total momentum initial plus the average external force times delta t equals the total momentum final. So this is the external impulse. And so the key idea in terms of defining your system is, what do you want to apply conservation of momentum to, and what do you want to regard as applying an external force? So I would say, as a general rule, you want to define your system to be everything that is not connected to the earth that is involved in the problem. That's usually going to make your life easier. The problem with including the earth as part of your system in a momentum conservation problem is that the momentum of the earth is sort of so gigantic that it's hard to quantify. You usually don't have the information you would need to include it. So I think that's the basic answer, is don't include the earth as part of your system for momentum conservation. And I'm guessing that your question comes in particular from problems like the Toyota, and I forget what the other vehicle brand was, where the two vehicles collide at right angles. And you're supposed to ignore this term of the external impulse during the time of the collision. And the reason that you're allowed to do that is that we're assuming that the delta t is small for a collision. And we are also can make the reasonable assumption that this is small, the average external force during the collision due to friction. So if we're talking about friction, then that average external force is small compared to the forces that the colliding objects exert on each other. So a counter example would be when the smart car runs into the brick wall. If we take the brick wall as being outside the system, which that's what I would encourage you to do, that is not exerting a small force, that's exerting a really big force. Whereas when the two cars collide, they're exerting huge forces on each other, and so the frictional force is small compared to them. And so that's why we're we can say that we're going to ignore that external impulse.
So for that, like, is T always going to be small?
I think for every problem that we have done in this class, it's going to be small. So including problems that are likely to appear on the exam.
Then the difference is just how big the force is.
Yes. So it's a similar consideration for defining your system for angular momentum, that again, you don't include anything that's fixed. Because so since you've asked this question, I sort of want to point out that for this problem that you had on the homework, where you had a disc and you had a piece of putty that was falling onto this protrusion, if you try to solve this using conservation of momentum, it doesn't work very well because the axis exerts a large external force during the collision. So that is to say that the piece of putty is exerting a big force downward on this disc, but we know that the disc doesn't move, and so therefore the axle, I said axis, but I meant axle, the axle must be exerting a large upward force on the disc to keep it from moving. And therefore, conservation of regular momentum is challenging in this case because this is sort of a large unknown force. So F av external delta t is non-negligible, but also unknown, or not easily known. At least you could probably figure it out. On the other hand, because that force is being exerted right at the axis around which we're considering rotation, it exerts no torque. And so when we're talking about the general law of the conservation of momentum, that would be Li, or L total initial, plus external torque average times delta t equals L total final. So this force, because the line of action of the force passes through the axis of rotation, exerts zero torque. So it's easy to apply conservation of angular momentum. It's a really good question, Emma. Continuing down our list, and feel free to jump in when you have other questions. Definition of angular momentum as a vector in terms of vector omega and in terms of vector r cross vector p.
Can we talk about that?
So L equals I omega if we're talking about something that's moving in a circle, circular motion, and L equals r cross p. This works for all motions, but it's easiest to use for linear motions. So the L equals r cross p, that's sort of the fundamental definition. So I could add a third little equal sign there. That's really the definition of angular momentum. And so that will always work, but it's easiest to use that version when things are moving in straight lines, and to use this version when things are moving in circles. So in terms of the vector nature, remember that r is a vector that goes from the origin to the point of where the object is. So let's say if we go back to this example of the disc with the piece of putty, and we're thinking about just the contribution to the angular momentum from the putty. Oh, I should say this one works best for point masses. Again, you could use that second one for any situation, but you'd have to divide it up into point masses, which gets difficult for a continuous object like a disk. So let's say if we were going to calculate just the angular momentum due to the putty, we would draw a radius vector from the axis out to the putty. So there's my radius vector r. There's my momentum of the putty just after it has hit, for example. Or no, let's say just before it has hit. And so to calculate the direction of that angular momentum, I would draw the two vectors tail to tail. And then to calculate the cross product, I put my fingers in the direction of r and fold them into the direction of p. And so that gives me an angular momentum that's pointing into the page. If I instead want to think about the angular momentum of the whole system, it's going to be rotating like this. So I would use this L equals I omega version. I curl the fingers of my right hand in the direction of rotation. So omega and L both point into the page.
Okay, yeah. So like for the like homework problems, like I guess I didn't really like, I only solved the problem like that because that's how the notes did it. But I guess I didn't really understand like where the equations came from.
Where these two equations for L come
Or
from?
like why, like, because I think we did have to use like those equations for at least one of the homework problems.
Sure. I mean, you have to use both of them for this problem that I've been using as an example. You have to use both equations, right? Because you were using the L equals R cross P to get the angular momentum of the putty just before it hits. And then you were using L equals I omega to get the angular momentum of the system after the putty hits.
So like even things that like aren't, I guess that was kind of a misconception of mine. So it's like even things that like aren't like it doesn't like make sense that like something moving in a straight line would have angular momentum.
Yeah. So one way to reconcile yourself to that is, let's say I've got a mass on the end of a string that's moving in a circle like this. And if I just think about it at one instant in time, at that instant, I can't really tell that it's moving in a circle. I just see it moving with some velocity v. And so, as far as I'm concerned, it's moving in a straight line, and yet we can also see that it's moving in a circle. And so that's in fact how we derived L equals I omega from this definition of L equals R cross P, was thinking about this situation and showing, okay, if I define I to be m times the average value of R squared, then I could rewrite L equals R cross P as this if something is moving in a circle. But it's a little bit confusing because of that name, I suppose, angular momentum. But just remember that this is really the basic definition of angular momentum, R cross P. And maybe this picture helps of just thinking about something moving in a circle does have an instantaneous velocity that, as far as anybody can tell at that instant, is moving in a straight line. Okay. Good questions. Continuing down our list. Yeah.
Oh.
Go ahead.
This is sort of, I don't know, like, is there a way to tell like when to use kinetic energy versus momentum to solve a problem?
Great question. Pretty simple answer, that if you're talking about collisions, you're going to use conservation of momentum. And the reason for that is that in a collision, most of the time, some of the energy gets converted into heat, which is difficult to quantify in many cases. So there's sort of a special case of elastic collisions, but remember, most collisions are not elastic. Most collisions, some energy is converted into heat. So our special case, and in our class, it's only for 1D elastic collisions. And there we used both conservation of momentum and energy, but you will not be asked to redo that. In other words, we sort of derived this very handy equation, VF equals 2VCM minus VI. And so we did that in class, and I'm not going to ask you to redo that on the exam, but you need to be ready to use that equation. But again, remember that that's just the special case. It has to be both a one-dimensional and an elastic collision. And I've told you guys explicitly, we're not going to be doing 2 or 3D elastic collisions. We're only going to be doing 2 or 3D collisions where things explode or stick together, which, to be frank, that's the main kind that matter. Does that answer your question? So if it's anything other than a collision, use conservation of energy, or at least try it. See if it gets you the answer. Most of the time it will.
Okay, thank you.
Mm-hmm.
So like in the homework problem from the last problem set where it was like the one disc like fell on top of the other disc, like that would be considered like an elastic collision.
That's an inelastic collision, because in that
Yes.
case, some of the energy gets converted into heat as the disks rub together and finally come to the same angular velocity. There you're using conservation of angular momentum, but it's kind of a similar idea that it'd be hard to apply conservation of energy because some of the energy is being converted to heat.
So is it still kind of like try to use conservation of energy?
Except for a collision.
Except for collisions.
Mm-hmm. Yeah. Okay.
Could you actually maybe talk more about like the equation that you just said, like BF equals 2BCM minus B initial?
Sure. So again, that's only for one-dimensional collisions. So for example, if I have, I don't know, some large object of mass m moving in this direction with velocity capital V, and maybe let's make things a little bit different. Let's have it be about to collide with a smaller object of mass little m that's moving with a velocity little v that's smaller than big V, and they're going to collide elastically. And we ask, what is the final velocity of both objects? And so let's call these objects 1 and 2. So the final velocity of object 2 will be twice the velocity of center of mass minus the initial velocity of object 2. The velocity of the center of mass is equal to the mass weighted average of the two velocities. So that'd be like this. In this case, so both velocities are to the right. So in this case, both capital V and little v are greater than 0. But bear in mind when you're using this equation that the velocities are allowed to be negative. So so velocities can be negative. This is not meant to be the magnitudes of the velocities, but actually positive or negative velocities. And we're using that convention because we're only applying this equation for one-dimensional collisions. So then plugging this equation for the velocity of center mass in here, we would get that the final velocity of object 2 is big M, big V, plus little m, little v over big M plus little m minus little v, because the initial velocity of object 2 is positive little v, and there's a minus sign here. We could simplify that further, but I'm not going to spend the time right now. Questions? So Emma, I'm not sure if that answers your question about explaining that equation further.
Yeah, so it's like kind of like a shortcut.
It is it's not just kind of, it is a shortcut that works in this one important special case of one-dimensional elastic collisions, and it contains already the ideas of conservation of energy and conservation of momentum. Okay. So again, as you guys have been doing, don't feel constrained to only ask questions about the topics that I'm highlighting. Differential equations, understand what a differential equation is. Don't get too worried about this. Remember that we only talked about differential equations for literally like 10 minutes. So this is literally the only thing that I might ask you about on the exam. I will not ask you to solve a differential equation, but I might ask you what is the definition of a differential equation. Mass on spring and equivalent systems, the equation for angular frequency. So there, even though we only derived that in the last 15 minutes of the class, we did use that earlier in our discussion of the molar heat capacity of solids. So you do want to know that. So maybe I'll just remind that here, square root of K over M. Connection between frequency, angular frequency, and period. Fluids, fluid pressure, and how it depends on depth for liquids. I probably shouldn't have put in for liquids because it actually works the same way for gases. It's a little bit more complicated for gases because especially when you're talking about large distances, the density depends on altitude, whereas for liquids, the density is pretty much fixed. Fluid drag, and again, we haven't talked much about this, but I expect you to understand that in the turbulent regime, the fluid drag force is proportional to the square velocity, whereas for laminar flow, and I shouldn't have used that technical term, what I should have said is non-turbulent. It's proportional just to the velocity.
Can you go over like turbulent and non-turbulent again?
So again, we haven't talked about them in detail, but when something is small or slow, so let's say if I've got a small bead that's moving slowly through the air, then the air can sort of displace around it in a very smooth way. But if I have something that's large or fast, and it's moving through the air, then there are sort of eddies that get created in the space behind it, and that's turbulence. So it turns out that that leads to this v squared dependence of the drag force on velocity. Oh, I just realized that, well, let's see, I'm just trying to remember. Yes, I did. Okay. I was trying to remember if I'd put terminal velocity on here because that's connected with those ideas of fluid drag. The kinetic theory of gases, be ready to reproduce the argument of how this leads to the ideal gas law. The idea of absolute zero. The ideal gas law in the chemist and physicist versions. Be ready to explain qualitatively for a solid and quantitatively for a gas why the heat capacity at constant pressure is greater than heat capacity at constant volume. Okay, equipartition theorem. Know it, including the caveat about quantum level spacing. Be ready to use it to estimate the molar heat capacity of a specified gas or solid. Know that for a diatomic molecule, there are only 2 rotational degrees of freedom, and understand roughly why. Understand why for gases with more than 1 atom per molecule, the above predictions are only valid at high temperatures. Understand why for some solids, the heat capacity at room temperature is lower than at high temperature, and be ready to predict which solid has a higher room temperature heat capacity based on hardness or effective spring constant and atomic mass. Okay, latent heat. We didn't talk about that much, but it's also not a very complicated idea. So might have a question about that. Terminal velocity.
What's
Again,
latent heat?
Latent heat is the extra heat you have to supply to a liquid to transform it into a gas. So we use that in our discussion of the comparison between reverse osmosis and distillation. Terminal velocity. Again, we didn't talk about it much, but it's also a fairly simple idea, so it might appear. Random walk. Be ready to reproduce the argument for a 1D random walk leading to RMS displacement proportional to the square root of the number of steps.
Can we just talk about like the big takeaways from random walks? Like I feel like we kind of spent like a while like driving it and stuff, but what's like the big like takeaways from that?
Well, we talked about three. So the really big takeaway is that that our XRMS is proportional to the square root of n. So that's sort of the most important thing. But then we also talked about how that means that your signal to noise ratio for an experiment is proportional to the square root of the number of trials or number of repetitions. And that when you're adding errors, the total error is equal to the square root of the individual error sources added in quadrature, meaning you square each error source, add them together and take the square root. So individual error average value. And this is average value of the total error. And then finally, that the RMS displacement was the square root of 2 times this constant, the displacement constant, diffusion constant times T. This equation we didn't prove. Einstein's diffusion equation, which we're about to get to here, but we have used this in a couple of concept tests. And in particular, we used it to show that we used reasoning to show that things that are small will have a large mobility and therefore diffuse a larger distance in a given time. So I'd say that those are the three big takeaways from the random walk.
Can we also go over terminal velocity? I feel like.
Sure. So the idea is that when something is starting to fall, let's say a human being, at first, the only force that's being applied to them is their weight, mg. But as they fall, so here their velocity is essentially 0 or very small. As they fall and start to build up speed, their velocity gets bigger, and therefore the force of air resistance on them gets bigger. And eventually it builds up to the point where the force of air resistance upwards equals the gravitational force downwards. So there's no net force on them. That doesn't mean they come to a stop. That means they stop accelerating. So when F air resistance equals mg, and here I'm talking about magnitudes, you have reached terminal velocity. So that's a pretty simple idea. Let's say if you were asked to calculate the terminal velocity, you'd have to be told, are you in the turbulent limit or are you in the non-turbulent limit? So for example, if non-turbulent, then we know that the air resistance is just proportional to the velocity. It's usually written as minus b times v. So when I write this, maybe I should put absolute value signs around the F air. So BV terminal would equal mg. And so you could solve that for the terminal velocity, for example, if you needed to. You'd have to be given the value of B. But
Okay, and so here, like the net force would be 0, right? At
correct.
terminal velocity. Okay.
Mhm.
Oh, good. Thank you.
Yeah. Okay, diffusion. We already talked about most of this. Osmosis, so the equation for osmotic pressure and the meaning of it. The energy needed for purification of water by reverse osmosis. I do expect you to understand what you learned in the 2 labs that we did since exam 2, which were the momentum lab, which I think that was covered more or less the same material as what we talked about in class, and the sound lab. In the sound lab in particular, you should understand that was a mostly qualitative lab, but you should understand what Fourier analysis is and also the connection between wavelength, speed, and frequency for traveling waves.
Can we talk a little bit about that too? Because I feel like though we did the sound lab, we haven't really, I don't know, haven't gotten back like I guess like the comments on it. So I like wasn't sure like, which parts I understood.
Okay, do you have specific questions or just kind of general ones?
First, do we need to understand how like does the speed of sound change based on like what bulk modulus it goes through or something, or do we not need to worry about things like that?
You don't need to worry about it, but it does. So just sort of for your general edification, the speed of sound, like it's faster in solids than it is in gases. And it's faster in liquids than it is in gases. And in a gas, it depends on the temperature. So the higher the temperature, the higher the speed of sound. But the main takeaway that I care about from that lab is that you understand that the velocity is the wavelength divided by the period. Sort of that's the main equation that I care that you understand about traveling waves.
Do we need to know like what would be the takeaway? Do we have any other takeaways about pitch or anything like that that we need to?
I think I want you to understand this general picture of the connection between when I'm drawing, let's say, the pressure, air pressure, which is the sound wave, minus the average air pressure. So these are the pictures that were in your lab manual. So as a function of time, if this is a pure sinusoid, then if I'm drawing the Fourier transform of this, so Fourier amplitude is what I'm now graphing on the vertical axis as a function, not of time, sorry, but of frequency. If that's a pure sinusoid, there would just be one peak on this. And it would be if this time, this period is capital T, then this will be at a frequency equals 1 over capital T. Whereas if you have a more complicated wave, so now pressure minus pressure average versus time, something more complicated like this, but still repetitive, that's going to give you a Fourier transform. So Fourier amplitude that will now have multiple peaks. So maybe for this one, let's say if this is the period T, then the fundamental will be at the frequency 1 over T, but then you have overtones. So let's call this F naught. This would be at 2F naught, 3F naught, etc. So all the other peaks are at multiples of that fundamental repeating frequency. Good. Okay. So that's the end of our list, but I would welcome questions either about things that were on that list or stuff from the material we covered for exams 1 and 2, or anything else.
Going back to the like random walks, I guess I'm still kind of confused on like the first part. So like, what is like the point of knowing that like X RMS is proportional to N?
Square root of N.
Yeah, square root of N.
So the main thing is first understanding this idea that when you're in a random walk, so you're starting at some point here, you're taking some steps in random directions and maybe of different lengths, but having some well-defined average length, that there is no change in your average position, but there is a change in your average distance away from the origin. You don't know whether it's going to be positive or negative, but it's likely as time goes on, you're going to move farther away from the origin. So that's part of the content of this. So you're likely to move away from the origin to the right or the left. Another important part of it, though, is that you're only moving proportional to the square root of the number of steps, which means usually proportional to the square root of time, not proportional to the number of steps. So you're sort of moving more slowly than something that's not moving randomly. And that should make sense. Other questions?
For the equipartition theorem, or like, will we ever be asked to find the heat capacity when, like, for example, a gas isn't at a high temperature? It'll only be in conditions where the equipartition theorem works, right?
I mean, yes, but I do expect you to understand this idea, because we spent a fair bit of time on it, that as you cool it from that high temperature limit, first the vibrations freeze out and then the rotations freeze out. So I might ask you, what's the low temperature limit of the heat capacity for a gas? Or what's the heat capacity in the limit that the vibrations have frozen out, but the rotations have not yet frozen out? And when it comes to solids, that freezing out, we talked about a sort of more with respect to solids, because in the case of solids, you're at room temperature, often kind of in the midst of that freeze out process. And so we want to sort of semi-quantitatively be able to describe how far along in that freezing out are you. And in particular in class, we talked a lot about that comparison between gold and diamond, and how, because the quantum level spacing for diamond is so much bigger, at room temperature, you're more frozen out, so the heat capacity is lower.
Thank you.
Sure. Other questions? Okay, I think we'll wrap it up here. I will, if in the other session there are some questions that come up that didn't come up here, I will alert you guys to that. So let me just write down the people that came to this one. And the exam, as is usually the case when I'm at this stage, I've written all the questions. I need to finalize it. It's really almost there. So it will be ready, let's say by 2:30 p.m. today. And I'll send you guys out an email when it's ready for you to download and take at your convenience. So, good luck.
About how
Yeah.
long is it? The time?
so again, I need to finalize that, but it will be either 3 or 3.5 hours with 2 10-minute breaks. All right, see you guys.